When we have just two types of individuals, what we're often interested in is the probability that an individual of a particular type can take over the population. And the variable we're going to use for a lot of that discussion is xi, which is that the probability that I individuals of the first type end up taking over the population. In other words, that if we start at I n minus I, what is the probability that eventually, through numerous jumps, we end up at state n 0. Okay, and the fixation probability is referred to as rho is given by x1. That's called the fixation probability, and that's particularly interesting because that's when we have a single mutant entering the population. What is the probability that they take over the population? The good news is that we have all sorts of analytic formula to study this. And that is given by this. Let me get that a bit higher up. Which says, given a birth-death process, which is what this is, when you just have two individuals, it's a birth-death process, the probability xi is given by that expression on the screen. But the cool thing is that in the case of a game, that we can actually write down what these probabilities are. And what they happen to be is the fitness of individuals of the second type, given a count of I individuals of the first, divided by the fitness of individuals of the first type. And so we can calculate xi by plugging this into there and there to obtain the probabilities of these things happening. Now, that's all rather vague and needs to be explained a bit more. So if I take as an example the hawk-dove game, so if we take the, try and leave that on the screen, the hawk-dove game. Oops. And if we consider n equals 3, and we're asking what is rho? So what is the probability of one individual one individual of the first type, so one dove taking over the population? As a reminder, the hawk-dove game has this matrix here. Two doves will share. A dove will get nothing from a hawk. A hawk will get, that's not quite true. A dove will get a low score from a hawk. A hawk will get a lot from a dove, and two hawks will get nothing from each other. So to be able to calculate this formula here for the case of n equals 3, we're essentially going to plug in those numbers. So I like to do this as a little table and say, all right, I need to know these fitness values f1 and f2 for different values of I. In the case n equals 3, there are essentially two values of I that I care about. I equals 1 and I equals 2. So I'm saying, all right, what is the fitness of individuals of the first type in a population where there is only one individual of the first type? And what is the fitness of individuals of the second type in a population where there are only one individual of the first type? And then the final thing that we're interested in is the ratio of those things. There. And so we can essentially calculate these things. So if I have one individual of the first type, they are going to get one time because they're going to meet that other hawk. They're going to get that hawk twice, so they're going to get a fitness of 2. And when there are two individuals of the first type, then they're going to get 1 when they meet the hawk. Remember, there's 3 individuals, and 2 when they meet the other dove to give us a value of 3. Fitness of the second type, so the hawks, Well, when there's only one dove, that means there's another hawk, so we'll get 3 once and 0 when they meet that other hawk, and they will get 6 when there's nothing but doves. And so our ratios just become 3 over 2 and 6 over 3, in other words, 2. Now, this gives us everything we need to plug into this formula here. And so we're interested in rho, which is x1. And so if I look at the numerator, that's a 1 plus the sum from j equals 1 to I is only going to 1, so there are no terms in this sum. So that's just a 0. Pardon me. And if we look at the denominator, it's a 1 plus the sum from j equals 1 to 2. So there's going to be 2 other terms here. And what I'm taking is the product of these lambda k's. And so the first one, j is just going to 1. So I just have the product of k equals 1 to 1 of gamma k, which is just gamma 1. So 3 over 2. And then here I've got my second term is when j is equal to 2. So I'm going from the product from k equals 1 to 2 of gamma k, which is 3 halves times 2. That is equal to 1 over 11 halves, which is equal to 2 over 11. So in a population of 3 individuals, the probability that a mutant dove takes over the population is 2 over 11. And what we can do is we can confirm these analytic results. We can confirm these analytic results by actually simulating the process. And here's a plot of the simulation, just over 100 repetitions, which is not a lot, pardon me, and the theoretic value says the n equals 3. There's the 2 over 11 that we just calculated by hand, and you can see that the theoretic value matches up very nicely with the simulations. And if we did more repetitions, it would actually match up perfect.